Take a deep breath in, and as you gently exhale, allow your body to settle completely into the soft, quiet support of your bed. Tonight, we are leaving the familiar bounds of Earth to drift through the calm expanse of the cosmos, arriving at a magnificent azure world where the laws of nature create a quiet, breathtaking symphony. We find ourselves floating peacefully before Neptune, the eighth planet from the Sun, orbiting in serene solitude at a staggering distance of 2.8 billion miles away. Here is something most people don't know. Because of this immense distance, the sunlight that warms your face on Earth takes just over 4 hours of silent travel through the vacuum of space to reach the tranquil blue atmosphere of this distant giant. By the time the sun's rays arrive here, they are but a gentle, distant glow, casting a twilight softness over the entire planet. As you observe this massive globe in your mind's eye, you can almost feel the profound stillness of the outer solar system, a place where time seems to slow down and the rush of everyday life fades into absolute silence. Neptune presents itself to you as a flawless sphere of deep, rich azure. What is fascinating about this color is its chemical origin. Neptune's upper atmosphere is composed primarily of hydrogen, making up about 80% of the air, along with 19% helium. But it is the trace amount of methane, just 1.5% of the atmosphere, that paints the planet in its signature hue. Methane molecules have a unique property. They absorb the red wavelengths of light from the distant sun and reflect the blue wavelengths back out into space. As you picture this cool, soothing blue washing over your vision, imagine the texture of these upper clouds. They are wispy and ethereal, drifting in a state of perpetual twilight. Despite its tranquil appearance from afar, this world is vast beyond human comprehension. Consider the sheer, comforting magnitude of Neptune. Its volume is so immense that you could comfortably fit about 57 Earths inside it. Yet, if you were to rest at the very top of these blue clouds, the atmospheric pressure surrounding you would be exactly 1 bar, identical to the comforting pressure you feel at sea level on Earth right now. It is as if this alien world offers a familiar, gentle embrace at its highest peaks. And as the planet spins, it does so with surprising grace. A single day on Neptune lasts only about 16 hours. This rapid rotation creates a soothing rhythmic momentum, a planetary heartbeat that hums quietly in the dark. Imagine yourself now, completely protected and weightless, beginning a slow, peaceful descent down through those blue methane clouds. As you drift lower, the quality of the light begins to change, deepening from a bright azure to a rich, enveloping indigo, and finally into a comforting, total darkness. You are passing through the outer atmosphere and entering what astronomers call the mantle of the ice giant. But the term ice here is a scientific convention, not a description of frozen glaciers. In planetary science, ices refer to compounds like water, ammonia, and methane. Deep inside Neptune, these elements do not exist as solid ice or thin gas, but rather as a dense, supercritical fluid. Imagine the sensation of moving through this fluid. It is thick, smooth, and heavy, offering a gentle cradling resistance, much like the feeling of being deeply submerged in a warm, quiet ocean. You are now descending into the zone of the diamond rains. This breathtaking natural process occurs deep within the planet's interior, roughly 4,300 to 5,600 miles below the visible cloud tops you just left behind. To understand the quiet miracle of what happens here, we must look at the extreme, transformative conditions of this depth. The pressure around you is now slowly increasing to approximately 1.5 million times the atmospheric pressure at Earth's sea level. The temperature, too, has risen significantly, reaching an incredibly intense 8,500 degrees Fahrenheit. While these numbers sound extreme, in the context of our journey, they represent a warm, protective crucible, a place where the fundamental building blocks of matter are gently coaxed into new, beautiful forms. Here is the profound truth of Neptune's deep interior. Under this specific combination of heavy pressure and intense heat, the methane molecules begin to change. A methane molecule, known chemically as CH4, consists of a single carbon atom bound to 4 hydrogen atoms. As the heavy, warm fluid presses in from all sides, these chemical bonds are quietly squeezed until they break. The 4 hydrogen atoms are stripped away, drifting gently into the surrounding ocean of fluid. This leaves the carbon atoms totally free. In the dark, silent depths of the planet, these lonely carbon atoms naturally seek each other out. Drawn together by the fundamental laws of chemistry, they begin to bond. They lock themselves into a rigid, incredibly stable three-dimensional tetrahedral structure, a crystal lattice. In doing so, these invisible atoms of carbon transform into solid diamonds. Picture this remarkable process happening all around you in the dark, pressurized fluid. Microscopic diamonds, born from the crushed remnants of methane gas, are crystallizing out of the fluid. Because these solid diamond crystals are vastly denser and heavier than the supercritical ocean of water and ammonia surrounding them, gravity takes hold of them. They begin to slowly, peacefully sink. This is the diamond rain of Neptune. It is not a violent storm, but a quiet, eternal precipitation of precious gems falling through a dark, warm, planetary ocean. Some of these sinking diamonds are small, perhaps only a few millimeters wide, resembling the gentle rhythmic patter of raindrops falling through the sky. But what is truly mesmerizing is that planetary physicists theorize these crystals can continue to grow as they fall. Over immense time scales, as they drift deeper and deeper into the planet, these diamonds may merge and accumulate, slowly forming massive, iceberg-sized chunks of solid diamond, gracefully sinking through the thick, viscous depths. You might wonder how we know this serene, unseen process is happening billions of miles away. It is thanks to the ingenuity of terrestrial scientists who managed to recreate this alien environment right here on Earth. At the SLAC National Accelerator Laboratory in California, researchers used an incredibly powerful instrument called the LINAC Coherent Light Source. This device is an X-ray laser, capable of generating pulses of light so intense and so fast that they can capture chemical reactions happening in a fraction of a billionth of a second. To simulate the methane inside Neptune, the scientists used a simple common plastic called polystyrene, which has the chemical formula C8H8. Polystyrene is made of the exact same 2 ingredients as methane, carbon, and hydrogen. In a marvel of modern physics, the scientists fired powerful optical lasers at the plastic, creating shock waves that briefly simulated the 1.5 million bars of pressure and the 8,500 degree heat found deep inside Neptune. In that fleeting fraction of a second, they watched as the carbon atoms separated from the hydrogen and instantly crystallized into nanodiamonds. They proved that the beautiful theory of diamond rain is a verified physical reality. As these diamonds fall through Neptune's mantle, they perform one more vital function for the planet. The friction of countless diamonds slowly sinking through the thick fluid generates a massive amount of heat. as the heavier diamond materials fall inward toward the planet's core and lighter fluids are displaced upward. This gravitational energy is converted into thermal energy. This gentle, internal friction is the secret behind a long-standing astronomical mystery. For decades, scientists observed that Neptune radiates 2.61 times more energy into space than it receives from the distant sun. It is a planet that creates its own warmth. The quiet, eternal falling of the diamond rain acts as a massive planetary engine, keeping the heart of the ice giant warm in the freezing depths of the outer solar system. You can sense that deep, irradiating warmth now, a subtle vibration echoing through the supercritical fluid, a comforting pulse of heat generated by the graceful descent of millions of crystals. And where do these falling diamonds eventually end their journey? They sink toward Neptune's absolute center. The core of Neptune is estimated to be roughly the mass of our entire Earth. It is a solid, incredibly dense sphere, composed primarily of iron, nickel, and silicates. Imagine the texture of this core, ancient heavy metals and rock, resting quietly at the center of the planet's gravitational well. Over billions of years, the sinking diamond rain slowly blankets this inner core, creating a thick, sparkling mantle of pure crystal, resting upon a heart of iron. As you float peacefully within this heavy, warm fluid, surrounded by the invisible, silent rain of diamonds, you can feel the slow, inevitable rhythms of the universe working in perfect harmony. There is no rush here. The formation of a single crystal, the slow descent through thousands of miles of liquid, the gentle generation of heat, all of it happens on a timescale that stretches far beyond human counting. It is a place of deep, undisturbed peace, where the immense pressures of the universe do not destroy, but merely organize chaos into perfect crystalline symmetry. Floating suspended within the heavy, warm molecular soup of Neptune's interior, surrounded by the invisible cascade of newborn crystals, we are witnessing a phenomenon that humanity was completely unaware of for nearly all of its existence. Long ago, the ancient Romans looked up at the sky and named this distant world after their god of the sea, and they simply observed a celestial body and gave it a name, entirely unequipped to know that billions of miles away, this sphere actually harbors literal, super-pressurized oceans of dense fluid hiding beneath its calm, azure clouds. The true nature of this magnificent giant remained an absolute secret until very recently in our history. Notice how the modern story of this blue globe begins not with the sudden glare of a telescope, but with the quiet, methodical scratch of a pen on paper. In the mid-19th century, a French mathematician named Urbain Le Verrier spent his days studying astronomical charts. He meticulously tracked the orbit of Uranus, noting gentle, unexplained irregularities in its path. Through pure mathematics, he predicted the gravitational pull of a completely unseen, massive, neighboring planet. On the hushed, a clear night of September 23, 1846, a German astronomer named Johann Galle pointed his observatory telescope into the dark, guided precisely by Le Verrier's calculations. Within a single degree of the predicted location, a faint, cool blue dot manifested in the eyepiece. In that serene moment of observation, Neptune became the very first planet in human history to be discovered entirely through the predictive power of mathematics, rather than through direct empirical observation. Consider the immense, humbling scale of time involved in our relationship with this world. Because Neptune resides at such a profound distance from the warmth of the sun, its journey through the solar system is incredibly slow and leisurely. It takes exactly 164.8 Earth years for the planet to complete a single orbital lap around our star. This means that from the moment Gala first laid eyes on that quiet blue dot in 1846, humanity patiently waited generations until the year 2011 for Neptune to finally finish its first full orbit since its discovery. It is a planet that measures time not in fleeting days, but in slow, majestic centuries. For more than 100 years following that initial sighting, the deep interior of the ice giant remained a total mystery, locked away beneath impenetrable layers of methane and hydrogen. It was not until 1981 that a planetary scientist named Marvin Ross, working at the Lawrence Livermore National Laboratory, published a groundbreaking paper in the scientific journal Nature. He was the very first individual to formally propose the concept of the diamond rains. Ross mathematically theorized that the sheer, crushing weight of the atmosphere could force carbon out of the surrounding methane molecules. For decades, it remained a beautiful theoretical dream, suspended in the realm of physics, much like Leverrier's original unseen planet. Picture the monumental, silent arrival of humanity's first mechanical emissary to this quiet world. On August 25, 1989, the Voyager 2 spacecraft gracefully glided past Neptune, passing within just 3,000 miles of the planet's northern pole. Gliding through the frigid, soundless vacuum at over 60,000 miles per hour, the small probe spent only a brief, tranquil window, observing the massive globe before continuing its outward journey into interstellar space. The radio signals it beamed back to our world, traveling perfectly at the speed of light. It took precisely 4 hours and 6 minutes to bridge the dark gap and reach the listening dish antennas on Earth. The data gathered during that brief, peaceful flyby completely transformed our scientific understanding. Voyager 2 confirmed that Neptune is incredibly massive, containing an overall mass 17.15 times greater than that of our own Earth. But the probe's most puzzling revelation involved a hidden, silent energy radiating from the planet. Instruments aboard the spacecraft detected a magnetic field that is wildly off-center and wonderfully asymmetric. Unlike the magnetic field of Earth, which aligns relatively neatly near our geographic north and south poles, Neptune's magnetic field is tilted by an astonishing 47 degrees away from its axis of rotation. Furthermore, the true source of this planetary magnetism is not located in the exact center of the core. It is offset from the planet's physical center by roughly 8,500 miles, creating a lopsided complex magnetic bubble that hums quietly against the solar wind. Scientists now believe that the gentle, endless descent of the diamond rain is intimately connected to this bizarre, tilted magnetic field. As billions of solid crystalline fragments slowly push their way downward toward the core, they physically drag and displace the thick, metallic-behaving fluids that surround them. Imagine this immense, slow-motion stirring. The falling diamonds act much like heavy stones, sinking through a thick syrup, gently displacing the conductive planetary broth around them. In this localized movement generates powerful dynamos, electrical currents born from the quiet friction of sinking gems. It is the rhythmic, downward migration of these crystals that pushes the planet's magnetic field completely askew, generating an invisible shield that arcs silently out into space. At this very moment, thanks to continued human curiosity, we possess an even deeper understanding of the chemical ballet happening in these dark depths. In 2022, modern physicists updated the classical diamond rain theory by introducing a crucial, previously overlooked element: oxygen. Neptune's mantle is not solely composed of carbon and hydrogen. It contains vast oceans of water, meaning there are millions of tons of oxygen molecules suspended in the heavy pressurized dark. To recreate this specific environment in a laboratory setting, researchers ingeniously turned to a common household material, PET plastic, scientifically known as polyethylene terephthalate. This is the exact same material used to manufacture ordinary plastic water bottles on Earth. PET contains a perfect balance of carbon, hydrogen, and oxygen, making it an ideal surrogate for the chemistry of the ice giant. What the researchers observed, fundamentally, changed the narrative of the diamond rains. They discovered that the presence of oxygen actually acts as a gentle, natural catalyst. Within the intense planetary pressure, oxygen naturally pulls hydrogen atoms away from carbon with far greater ease than pressure alone. This means that diamonds can form and crystallize at significantly lower pressures and temperatures than previously thought. The oxygen smoothly guides the carbon out of its molecular bonds, accelerating the birth of the crystals in the dark. Think of a fresh analogy for the bizarre state of matter surrounding these newly born jewels. As the carbon separates and hardens into perfect diamonds, the remaining oxygen and hydrogen are squeezed into an exotic, heavy phase of matter known as superionic water. Imagine a dense molecular sponge made entirely of solid, glowing oxygen. In this superionic state, the oxygen atoms lock together to form a rigid, unmoving crystalline grid. Meanwhile, the hydrogen ions melt into a completely fluid state, flowing freely through the microscopic spaces of the oxygen cage, like water seeping through porous rock. This creates an environment that defies our everyday understanding of physics. The superionic water is exceptionally hot, heavily pressurized, and highly conductive, humming with a quiet electrical charge. As the heavy, pristine diamonds form, they slip silently through this electrified, cage-like fluid. The textures here are a study in perfect contrasts. The absolute sharp rigidity of the solid diamond crystals, passing smoothly through the heavy, glowing mesh of solid oxygen and liquid hydrogen. So, as you rest and visualize this unseen world, you are observing a multi-layered, harmonious choreography of physics and chemistry. Heavy, perfect diamonds are constantly crystallizing with the gentle assistance of oxygen, sinking gracefully through a thick, conductive matrix of superionic water. The friction and physical displacement of their eternal descent softly stir the heavy fluid, powering an invisible, a tilted magnetic field that sweeps out to touch the absolute stillness of space. The rhythm of this distant planet, the slow crystallization, the steady sinking, the centuries-long orbit, continues its peaceful, unhurried cycle, totally undisturbed in the quiet dark of the solar system. To comprehend the slow, majestic descent of these crystals through the deep interior of the ice giant, we must first understand the invisible pulling force of this enormous world. It might surprise you to learn that the gravitational pull at Neptune's upper cloud tops is strikingly similar to our own familiar environment. It measures exactly 1.14 times the gravity of Earth. If you could somehow stand on a platform, resting on those blue upper clouds, a person who weighs 100 pounds at home would weigh just 114 pounds here. It is a gentle, a completely manageable tug. You would feel only slightly heavier, as if wearing a thick, comforting winter coat. Yet, deep inside the mantle where the diamond rain forms, this familiar gravity interacts with materials of vastly different weights. The density of a pure diamond is precisely 3.51 grams per cubic centimeter. The surrounding supercritical fluid, however, is much lighter, possessing a density similar to Earth's oceans, fluctuating around 1 to 1.5 grams per cubic centimeter. Because the crystal is more than twice as dense as the surrounding liquid ocean, buoyancy dictates a simple rule: the heavier object must sink. Think of how a smooth, heavy river stone drops through a quiet pond. Gravity steadily pulls the stone downward, pulling it away from the surface. However, the supercritical fluid inside Neptune offers intense, thick, viscous resistance. Imagine dropping a small, heavy coin into a tall glass jar filled with thick, warm honey. The coin does not plummet violently. Instead, it oozes downward with a sluggish, mesmerizing grace, fully supported and slowed by the heavy liquid. The diamonds inside this planet fall at a similarly relaxed pace, traveling downwards at an estimated speed of only a few millimeters per second. It is a descent that requires immense patience, entirely unhurried by the rapid spinning of the atmosphere far above. At the microscopic level, the transformation of this falling material is a marvel of natural architectural efficiency. Consider a simple yellow wooden pencil resting on a desk back on Earth. The soft, dark core inside that pencil is made of graphite, which is composed entirely of pure carbon. Graphite ranks at a mere 1 on the Mohs hardness scale. It is so fragile and loosely bound that it easily flakes away just by rubbing it against a piece of paper. The heavy gems forming within Neptune are composed of the exact same carbon atoms found in that soft pencil lead. The profound difference lies entirely in the physical arrangement of those atoms. Under the immense pressure of the planetary depths, the atoms are forced to lock together into a face-centered cubic crystal lattice. You can visualize this intricate shape like an incredibly sturdy, interlocking steel scaffold used in the framework of a towering skyscraper. Each individual carbon atom forms tight, unyielding covalent bonds with 4 of its immediate neighbors, sharing electrons in a rigid, unbreakable grip. And this simple structural shift instantly elevates the material from a delicate powder to a perfect 10 on the Mohs scale, creating the hardest known natural substance in the universe, all from the very same ingredient. Observe the sheer, humbling volume of this hidden precipitation. Neptune's overall physical diameter stretches to an impressive 30,598 miles across, rendering it nearly 4 times wider than Earth. Within this massive spherical space, the specific mantle layer where the diamond rain crystallizes and falls is extraordinarily thick. Planetary models estimate this distinct chemical zone spans a staggering depth of up to 6,200 miles. To put that immense scale into everyday perspective, if you took the entire planet Earth, measuring from the crust, down through the rocky mantle, straight through the molten outer core, and right into the solid iron center, our entire homeworld measures just under 8,000 miles across. The diamond-producing shell of Neptune is nearly as thick as our entire planet. Millions of miles of quiet, continuous crystallization are happening within a planetary layer large enough to swallow Earth whole. As you mentally accompany these slowly sinking gems, realize that the environment surrounding you looks nothing like the clear waters of our home world. The supersonic water we explored earlier does not resemble the transparent, sunlit oceans of the Pacific or the Atlantic. Under these extreme conditions of heat and pressure, the water molecules behave differently, becoming entirely opaque. The fluid is an impenetrable jet-black void, completely blocking any form of light. It is a darkness far more profound than the very bottom of the Mariana Trench. Yet, this lightless, heavy ocean is vibrating with intense thermal energy. The temperature gradient down here is incredibly steep, near the upper boundary of the mantle, The fluid rests at a blistering 2000 Kelvin. As the diamonds sink deeper toward the core, the surrounding temperatures climb rapidly, reaching nearly 7000 Kelvin. What happens to the excess heat generated by the slow, viscous friction of the falling stones? This brings us to a highly unique physical property of the gems themselves. Diamond is an exceptional thermal conductor, significantly more efficient at transferring heat than almost any heavy metal we use on Earth. In fact, a pure diamond conducts heat approximately 4 times better than the copper wiring hidden inside the walls of your home. Imagine placing a cold silver spoon into a steaming ceramic cup of hot tea. Within seconds, you can physically feel the warmth traveling up the metallic handle, moving efficiently right into your fingertips. The sinking diamonds act precisely like millions of microscopic, highly efficient spoons. As they drift down into the hotter regions of the mantle, they rapidly absorb the intense heat of the lower depths and evenly distribute it throughout the cooler upper layers. They ensure a smooth, steady, harmonized flow of thermal energy throughout the opaque mantle, constantly balancing the internal temperature of the giant world. Finally, consider the unseen soundscapes of this hidden, high-pressure realm. Sound, as we know it, requires a physical medium to travel through, and the speed at which it moves depends entirely on the density and rigidity of that material. On our planet, when someone speaks or a bird sings, that acoustic energy travels through the thin air at roughly 343 meters per second. But within the ultra-rigid, tightly packed structural lattice of a diamond, acoustic waves behave very differently. Sound travels through this precious stone at an astonishing 12,000 meters per second. That is over 35 times faster than sound moving through our atmosphere. If you were to gently tap a solid block of this crystalline material, the vibration would zip from one end to the other almost instantaneously. Think of the old childhood trick of pressing your ear to a steel train track. Long before you can see the approaching locomotive or hear it through the air, you can hear the deep metallic humming of the train vibrating through the dense steel. The diamonds slowly falling through Neptune act just like those long steel tracks. They serve as perfect high-speed acoustic conduits for the deep, resonant vibrations of the planet's core. Every shift of heavy fluid, every slow turn of the magnetic dynamo, echoes instantly through the falling crystals, creating a silent, high-speed symphony of physical vibrations traveling through the warm, dark liquid. Surrounded by this gentle, heavy descent, we witness a world perfectly balanced by its own extreme conditions. The thick, viscous, honey-like resistance of the ocean slows the falling stones, while their rigid, skyscraper-like internal structure allows them to carry heat and vibration effortlessly through the dark. It is a masterpiece of planetary engineering, functioning perfectly and smoothly without any need for sunlight or human observation, quietly maintaining the steady heartbeat of the distant blue sphere. As we trace the path of these crystalline acoustic waves through the dark, heavy ocean, it becomes essential to understand our place in this broader cosmic neighborhood. For a long time, astronomers grouped our outer solar system neighbors, Jupiter, Saturn, Uranus, and Neptune, under the single broad umbrella of gas giants. However, in the 1990s, scientists realized this classification was fundamentally incomplete. Jupiter and Saturn are primarily composed of hydrogen and helium, closely matching the chemical composition of the Sun. Conversely, Neptune and Uranus contain a much higher fraction of heavier elements, each specifically oxygen, carbon, nitrogen, and sulfur. This distinct chemical makeup led astrophysicists to create an entirely new formal category: the ice giants. Furthermore, the mass of Neptune's visible gaseous atmosphere only accounts for about 10 to 20% of its total mass. The vast majority of its bulk lies hidden beneath the clouds, residing entirely in the heavy, warm fluid mantle we are currently exploring. Reflect on the primary ingredient fueling this majestic hidden precipitation: carbon. It is the fourth most abundant element in the known universe by mass, forged in the intense, crushing hearts of dying stars, long before our solar system even existed. Now, bring your awareness to your own physical form, resting quietly in your bed. Your body is intimately tied to the exact same stellar history. By mass, the human physical structure is approximately 18.5% carbon. Every single living cell, every twisted strand of your DNA, and the protective, flexible membranes surrounding your neurons rely entirely on the stable, versatile bonding capabilities of this specific element. Furthermore, isotopes help tell the story of this connection. On Earth, a stable isotope known as carbon-12 makes up precisely 98.9% of all naturally occurring terrestrial carbon. The fundamental atomic building blocks that construct your muscles and organs are virtually identical to the atoms currently being squeezed into flawless gemstones billions of miles away. You and this distant blue world share a profound, unbroken atomic kinship, woven from the same ancient cosmic dust. Notice the steady, calming rhythm of your breath right now. With every gentle exhalation, your lungs release carbon dioxide into the quiet, cool air of your room. An average resting human breathes out roughly 1 kilogram of carbon dioxide every single day. The carbon atoms you release gently float away, rejoining the Earth's natural biological life cycle, perhaps to be absorbed by a nearby tree or carried across the ocean by trade winds. On Neptune, however, the fate of this element is dictated by sheer physical confinement rather than biological circulation. In the realm of terrestrial chemistry, the carbon-carbon single bond is remarkably strong, possessing a bond dissociation energy of about 348 kilojoules per mole. It takes immense concentrated effort to break or reshape it in a laboratory. Yet, the deep planetary pressures effortlessly snap and reconfigure these bonds. While your exhaled breath gently dissipates into the thin, comforting atmosphere of a terrestrial night, Neptune's carbon is continuously captured, folded, and compressed into unbreakable perfection. It alters our perspective to realize that the same element, providing the soft flexibility of organic life on Earth, creates the most rigid, unyielding structures in the outer solar system. When we consider diamonds on our home planet, we often associate them with small, carefully measured gems held in the palm of a hand. Earthly jewelers use a standardized unit of mass, called a carat, which is precisely defined as exactly 200 milligrams. Furthermore, terrestrial diamonds frequently contain microscopic flaws, tiny mineral inclusions of nitrogen or boron, trapped within the crystal lattice during their chaotic, violent formation in the Earth's rocky crust. By contrast, planetary geologists suspect that the continuous uniform sorting process deep inside the ice giant creates structures of staggering, flawless purity. Because the hydrogen is completely stripped away by the presence of oxygen and unimaginable pressure, what remains sinks as a pristine, uncontaminated crystal. The temperatures here also defy our everyday logic. Carbon's melting point at standard Earth atmospheric pressure is exceptionally high, sitting around 3,550 degrees Celsius. Inside Neptune, however, the overwhelming pressure utterly prevents the material from melting into a liquid forcing it to remain in a solid state despite the intense ambient heat. Instead of fractions of a carat, these pure structures merge into monolithic formations that could theoretically weigh millions of tons each, slowly coalescing in the heavy dark. Visualize a grand, silent hourglass, measuring the lifespan of the solar system. Instead of fine, white sand slipping through a narrow glass neck, this planetary hourglass is filled with heavy, sinking diamonds. As they migrate downward through the thick mantle, they are slowly building up around the planet's solid rocky core. The physical radius of Neptune spans exactly 24,622 kilometers from its very center up to its wispy upper atmosphere. Over the course of billions of years, this steady accumulation of carbon forms a thick, sparkling shell, wrapping tightly around the metallic core. This is not just a temporary weather event. It is a permanent geological restructuring of the planet's interior architecture. The falling gems are steadily transferring mass from the upper layers down to the deepest center. Eventually, in the unfathomable distant future, the mantle will fully deplete its supply of methane. The very last diamond will form, sink, and settle, completing a planetary-scale sorting process that has lasted since the dawn of our solar system. The hourglass will empty, leaving behind a core encased in miles of perfectly still, solid crystal. What makes this quiet internal evolution so significant is how common it might be across the wider galaxy. In recent years, data from the Kepler Space Telescope revealed a startling truth about exoplanetary demographics. The most common type of planet found orbiting other stars is not a small, rocky world like Earth, nor a massive gaseous sphere like Jupiter. The Milky Way is overwhelmingly populated by a class of planets known as sub-Neptunes, worlds just slightly smaller than our blue neighbor, but rich in the exact same volatile ices and heavy elements. This astronomical discovery means that the peaceful, hidden precipitation we are observing here is likely a highly universal phenomenon. Across billions of alien star systems, in the heavy, warm darkness of countless exoplanets, carbon is naturally being squeezed out of dense molecular oceans. A steady, unseen rain of precious stones is falling throughout the galaxy right now. It is a quiet, continuous rhythm echoing across the light years, a comforting reminder that the universe operates on predictable, elegant rules of chemistry and physics, no matter how far we travel from home. At the absolute center of all this majestic activity lies Neptune's core, which possesses a temperature estimated to be around 5,400 Kelvin. To place that staggering number into perspective, this is approximately 9,260 degrees Fahrenheit, a heat remarkably similar to the bright, glowing surface of our sun. On our home planet, the internal warmth of the Earth is generated largely by the radioactive decay of heavy elements like uranium and thorium buried deep in our rocky mantle. But this ice giant utilizes a completely different mechanism to maintain its internal fires. The gravitational separation of elements, the simple eternal act of heavier materials dropping toward the center while lighter fluids are displaced upward, releases enough gravitational potential energy to keep the planet's heart roaring with warmth, when the sinking diamonds are quite literally feeding the planetary furnace. They ensure that even in the freezing, sunless outer edges of our solar system, the core of the planet remains vibrant, warm, and endlessly active. Feel the comforting weight of gravity holding you gently to your bed, just as it guides the carbon atoms toward the center of the ice giant. The same physical forces are at work everywhere, organizing matter, distributing heat, and maintaining balance. Whether it is the quiet exhalation of carbon from your lungs or the monumental descent of crystalline structures through an opaque supersonic ocean, the rhythms of nature continue their flawless, unhurried cycles in the peaceful dark. At this very moment, as the heavy carbon crystals continue their unhurried migration toward the core, we can shift our awareness outward, floating gently back up through the dense, supercritical ocean to explore the sensory boundaries of this magnificent globe. Moving upward, the crushing pressures gradually soften, and the opaque, supersonic liquid seamlessly transitions back into a thick, swirling gas. Here in the troposphere, the environmental conditions create a totally unique tapestry of temperatures, textures, and scents that define the outer shell of the ice giant. Scientists discovered that the extreme chill of Neptune's upper atmosphere reaches a staggering negative 214 degrees Celsius, which is equivalent to negative 353 degrees Fahrenheit. This specific atmospheric layer, known as the tropopause, is the coldest region on the entire planet. If you could safely extend a hand into this biting absolute cold, you would not feel the sharp sting of a terrestrial winter wind. Instead, because the gas here is incredibly thin and lacks the dense moisture of earthly air, the temperature would register as a profound, sterile numbness. An environment entirely stripped of radiating heat, suspended in a state of perfect deep freeze preservation. Notice how the signature blue hue of the planet is actively manufactured by the behavior of light hitting this freezing gas. The scientific mechanics of this color rely on a process heavily influenced by the presence of atmospheric methane. As the faint, distant sunlight finally arrives, the methane molecules act as a highly selective optical filter. These molecules naturally absorb light wavelengths longer than 600 nanometers, which correspond to the red, orange, and yellow segments of the visual spectrum. By capturing these warmer tones, the atmosphere perfectly scatters the remaining short wavelength light, the deep, calming blues and indigos, bouncing them gracefully back out into the void of space. You are drifting through a massive spherical prism that perpetually filters out the harshness of daylight, leaving only a soothing oceanic glow. Consider the unseen chemical aromas swirling gently through these upper cloud decks. If a traveler were somehow able to safely breathe this frigid mixture, the olfactory experience would be distinctly layered, driven by the varying condensation temperatures of different gases. In the highest, wispiest clouds, trace amounts of hydrogen sulfide exist in a frozen state. On our homeworld, hydrogen sulfide carries a rich, pungent, earthy aroma. Drifting slightly lower, as the atmospheric pressure mildly increases, the clouds are composed heavily of frozen ammonia crystals. Ammonia possesses a sharp, clean, deeply clarifying scent, much like the sterile tang of medical-grade cleansers. These distinct chemical bands do not mix violently. Rather, they stack neatly atop one another, like the precisely baked layers of a delicate pastry, organized entirely by their specific freezing points. What is happening now, in these aromatic, colorful clouds, is a demonstration of pure, unimpeded motion. The zonal winds wrapping around Neptune are the fastest recorded anywhere in the solar system, traveling at astonishing speeds of up to 2,100 kilometers per hour, or roughly 1,300 miles per hour. Yet, because these high-altitude gases are exceptionally thin, they do not roar or tear through the sky with the destructive force we associate with terrestrial gales. Supersonic wind flowing through a low-density environment moves with an eerie, total silence. To understand the why behind these mesmerizing speeds, we must look at the physical topography, or rather, the complete lack of it. On Earth, rushing air constantly collides with jagged mountain ranges, sprawling forests, and heavy ocean waves. These physical structures generate massive amounts of aerodynamic friction, continuously dragging and slowing the atmosphere. Neptune possesses no solid crust. The gases flow over a slick, entirely frictionless fluid interior. Think of a flawlessly polished, endless Olympic ice rink. If you slide a smooth, heavy puck across that perfect ice, it encounters virtually no resistance, allowing it to glide indefinitely. The supersonic winds of this ice giant glide in much the same way, coasting eternally around the globe on a bed of frictionless vapor. Picture this atmosphere rotating, but not as a single solid object. Because it is composed of free-flowing gas, Neptune experiences the most extreme differential rotation of any planet orbiting our Sun. The thick equatorial regions take roughly 18 hours to complete a single, leisurely rotation. However, the magnetic poles spin at a significantly faster rate, completing a full turn in merely 12 hours. This massive discrepancy in speed causes the bands of gas to slide past one another in a smooth, continuous shear. This latitudinal wind shear is the driving force behind the planet's majestic, slow-moving atmospheric eddies, where the most famous of these was the Great Dark Spot, an enormous high-pressure system completely large enough to swallow the entire planet Earth. Unlike the low-pressure, chaotic cyclones that bring rain to our terrestrial coasts, this colossal feature was an anticyclonic storm. Anticyclones are characterized by high atmospheric pressure and slow, outward-flowing winds. Instead of a violent vortex, the Great Dark Spot functioned as a massive, stable atmospheric plateau, a peaceful, churning carousel of dark blue gas smoothly rotating through the lighter azure clouds, completely harmless and utterly hypnotic in its steady rhythm. Deep within the invisible architecture of the planet's magnetic field, another fascinating sensory phenomenon occurs, entirely disconnected from the physical winds. And the planet's lopsided magnetosphere traps highly energized plasma particles. As these charged particles interact with the magnetic field lines, they generate electromagnetic plasma waves. Astrophysicists refer to these specific emissions as Whistler waves. The scientific curiosity behind Whistler waves lies in their unique frequencies. These electromagnetic pulses vibrate at rates between 1 and 10 kilohertz. By pure coincidence, this specific frequency range perfectly overlaps with the natural auditory range of the human ear. When the Voyager 2 spacecraft passed through the magnetosphere, its specialized plasma wave antennas intercepted these emissions and translated them directly into audio recordings. The resulting sound does not resemble static or a low rumble. Rather, it sounds exactly like a chorus of gentle, descending musical notes, or the soft sweeping chirps of tropical birds gliding through a quiet canopy. The reason these plasma waves produce a descending pitch is a beautiful quirk of wave physics. Higher frequency waves travel much faster through the energized plasma than their lower frequency counterparts. Therefore, when a cluster of these electromagnetic waves washes over a detector, the high, crisp notes arrive first, immediately followed by the slower, lower tones. This creates a soothing, rhythmic, cascading sound, a literal planetary song echoing silently through the vacuum of the outer solar system. As you rest, imagine the gentle complexity of this environment. The uppermost shell is a freezing, biting domain, tinted by the precise absorption of red light, carrying the layered, crisp scents of ammonia and sulfur. Silent, frictionless winds glide eternally across an invisible liquid surface, carving massive, stable anticyclonic plateaus the size of Earth. Above it all, the magnetic field sings a soft descending melody of chirping plasma waves. Yet, this entire atmospheric ballet represents just a fraction of the planet's true self. The gaseous envelope slowly thickens, its density gradually increasing until there is no definitive splash, no solid boundary, just a smooth, imperceptible transition back into the heavy, dark mantle. This deep fluid layer we explored earlier, where the carbon atoms are crushed into flawless rigidity, makes up roughly 65 to 70% of the planet's total mass. The silent winds, the blue clouds, and the chirping magnetic fields are merely the delicate sensory wrapping paper enclosing a vast, heavy, super-pressurized engine of liquid and falling gems. The balance between the freezing, hyper-fast exterior and the warm, slow, heavily pressurized interior operates in an endless, flawless equilibrium, requiring absolutely nothing but the quiet passing of time. To fully appreciate the magnificent equilibrium of this distant ice giant, we must turn our attention to the grand, slow-motion processes unfolding in the quiet space just beyond the blue clouds. Stretching outward from the upper atmosphere, Neptune possesses a delicate, faintly glowing ring system. First definitively observed by Earth-based telescopes during a stellar occultation in 1984. These rings operate through a continuous, step-by-step mechanical progression. The outermost band of dust and ice is known as the Adam's ring, and it is uniquely structured. Instead of a uniform, smooth loop of material, the Adam's ring features 5 distinct, densely packed arcs of matter. Astronomers have named these separate clusters Courage, Liberté, Égalité 1, Égalité 2, and Fraternité. The process that keeps these dense arcs from slowly spreading out and dissolving into the rest of the ring is a masterpiece of gravitational choreography. A small dark moon named Galatea orbits exactly 1,000 kilometers inside this specific ring boundary. Step by step, Galatea's gravitational pull creates a perfect 42 to 43 orbital resonance with the ring particles. Every time the moon completes exactly 42 orbits, the dust particles complete exactly 43. This repeating, sequential alignment traps the floating material in a gravitational pocket, shepherding the dust into tidy, permanent clusters that sweep endlessly through the dark. Observe the physical composition of these rings. They are incredibly faint, reflecting merely 3% of the distant sunlight that strikes them. The sequence of events creating this deep, reddish-black hue is a chemical transformation known as radiation darkening. The rings originally contain microscopic specks of highly reflective methane ice. However, out here in the vacuum of the solar system, these ice particles are constantly bombarded by high-energy cosmic rays. When a cosmic ray strikes a frozen methane molecule, it sequentially breaks the chemical bonds holding the structure together. Over the course of millions of years, the lighter hydrogen atoms gently boil away into space. What remains behind are complex, heavy carbon polymer chains. This gradual, microscopic cooking process systematically transforms bright, reflective frost into a dark, charcoal-like dust, absorbing the light of the sun. Down on the planet beneath these rings, another long-term progression slowly unfolds. Neptune's rotational axis tilts at precisely 28.32 degrees. This structural slant is remarkably similar to Earth's own 23.5-degree tilt. Because of this specific angle, the ice giant experiences 4 distinct seasons as it travels. However, because one complete sprawling orbit requires almost 165 Earth years to finish, the passage of a single planetary season unfolds over a staggering 40 Earth years. Currently, the southern hemisphere of the planet is tilted gently toward the distant sun, bathed in a multi-decade, continuous summer. This relentless, 40-year exposure to weak solar radiation creates a highly specific thermal progression. As the South Pole absorbs this steady, low-level energy, the local atmospheric temperature slowly climbs. At the very top of the stratosphere, directly above the southern pole, the temperature eventually peaks at exactly 10 degrees Celsius, warmer than any other location in the planet's upper atmosphere. This specific 10-degree margin acts as a precise thermal key. The gradual warming alters the local gas dynamics just enough to allow trapped methane to break through its atmospheric confines. Slowly, the methane gas rises upward from the lower troposphere, gradually spilling over the temperature boundary and flowing out into the upper stratosphere. It is a planetary exhalation, a slow, methodical release of gas triggered by a summer that lasts for decades. Looking further outward, we witness the ultimate expression of a long-term cosmic process by observing Neptune's largest moon, Triton. Triton performs a mechanical action found nowhere else among the large moons of our solar system. It orbits in a retrograde motion. It travels around Neptune in the exact opposite direction of the planet's own rotation. This backward movement initiates a steady, billion-year sequence of orbital decay. The opposing forces of the planet's rotation and the moon's backward orbit create immense tidal friction. This friction acts as a slow, invisible cosmic brake, systematically sapping Triton's forward momentum. Step by minute step, the massive moon is falling. It drops steadily closer to the blue clouds at a measured, unyielding rate of approximately 3.6 centimeters every single year. Planetary physicists have precisely charted the final outcome of this gradual descent. In roughly 3.6 billion years, Triton will cross an invisible fatal threshold known as the Roche limit. Upon crossing this boundary, the tidal pull on the near side of the moon will overpower the internal gravity, holding the sphere together. Through a sequence of immense structural failures, Triton will be systematically stretched and torn apart. The resulting trillions of icy fragments will slowly flatten and spread around the equator, forming a spectacular, massive, new ring system that will one day rival the current rings of Saturn. Deep inside the planet, far below the blue clouds and the dark rings, the ultimate sorting process of the ice giant continues in absolute darkness. At depths where the atmospheric pressure reaches up to 2 million bars, carbon is not the only element being compressed. Helium gas undergoes an identical separation process. The overwhelming pressure systematically pulls the helium atoms away from the surrounding hydrogen matrix. The freed helium condenses into microscopic heavy liquid droplets. Sequentially, these droplets begin their own downward migration. As they sink heavily toward the rocky core, they gradually release latent heat, providing an additional steady source of thermal energy to warm the deep interior. The internal workings of this massive world are entirely defined by this elegant, continuous process of sorting and settling. The heaviest elements, the pure carbon diamonds and the dense helium droplets, gradually fall downward, drawn to the absolute center. Meanwhile, the lighter elements, the warm fluids and the escaping methane gases, slowly rise toward the surface. Everything is moving toward its natural resting place. This quiet, sequential process of heavy things settling and light things dissipating mirrors the exact biological progression your own body undergoes as you prepare for sleep. Just as the distant ice giant slowly sorts its elements in the dark, your physical form is currently progressing through its own ancient, methodical phases of rest. Notice how the physical descent into sleep happens sequentially. The heart rate gradually slows down, step by step, dropping its beats per minute until it finds a steady, low-energy rhythm. The core body temperature lowers by a fraction of a degree, shedding the heat of the waking hours, just as the planet radiates its warmth into space. Metabolic processes shift smoothly from active energy consumption into a quiet phase of cellular repair. As your body physically settles into the mattress, gravity pulls the tension out of your muscles. The heavy accumulated fatigue of the day sinks completely downward, draining smoothly out of your shoulders, your arms, and your legs, disappearing into the soft support beneath you. At the same time, the light, fleeting thoughts of the day, the active planning, the rapid ideas, the lingering conversations, gradually rise up and evaporate from your active mind, much like the thin methane escaping into the stratosphere. The sorting is complete. Your mind is quiet, and your physical form has reached its perfect, heavy center of gravity. I am completely supported by the surface beneath me. My breathing is slow, steady, and effortless, and the events of the day have gently faded away. Every muscle in my body has released its tension. I am stepping naturally into a state of deep, restorative rest. My mind is clear, calm, and perfectly still. The natural rhythms of my body are guiding me into sleep. I welcome the quiet and the dark. I am entirely safe, entirely peaceful, and entirely relaxed. I surrender to the slow, heavy pull of rest. I am drifting gracefully into a quiet, dreamless space. My thoughts are quiet. My body is still. I am at peace. Good night.